Hello, my name is Valentin Starlinger, and I'm glad that I can join you here today. I'm going to present you a machine learning benchmark to assess the environmental impact of cars, a work I did together with Cristina de la Lope and Debarghya Ghoshdastidar. I want to start by introducing you to life cycle assessments. So what is a life cycle assessment? Life cycle assessments, or LCAs, are a scientific method to determine the environmental impact of products or processes. So this is done by looking at the whole life cycle of a product, from raw material production, manufacturing, up to the use phase and the disposal of the product, as well as all the transportation necessary in between. For each of the phases, information is gathered either from primary sources such as interviews or measurements, or secondary data from literature. However, due to the complexity of today's products, often simplification needs to be made by defining system boundaries that state what isn't included into the analysis. Once the system boundaries are set and the data is gathered, the process graph containing all the individual steps throughout the life cycle can be drawn. In this simplified graph here, you can imagine this to be the process tree of a car. Each of the boxes would correspond to a specific process. The boxes are connected via input and output flows. The input flows specify the resources needed for the process. The output flows specify the results of the process. So this will be the product, as well as all the chemical substances that are emitted into the environment during the process. The slide here says parameterized LCA, which is a special case of LCAs, where such a model is not only done for a specific single product, but is parameterized so that it can be applied to various use cases. So this means if we take this model of a car, for instance, you might have a setting where you can adjust the base glider mass in the manufacturing process or the total lifetime kilometers in the use phase. And we will be using that later. So once you have this model set up, you can then calculate the impact results for many different impact categories. The model will give a list of all chemicals emitted into the environment by the entire model throughout the life cycle, and then different standardized calculations are used to turn those emitted chemicals into specific environmental impacts. So if you look at the right-hand side, here you can see an example of how these results would look like. For instance, for the impact category climate change, the results are represented in CO2 equivalents. This is done so that you get a single number that is easily comparable. And you can also see here the results for water depletion for two different cars. The impact is further attributed to different parts of the vehicle and the production, such as emissions from direct exhaust or maintenance. And you can see that the attributions vary a lot between different impact categories. So now that we know what a LCA is and what results it gives, there are two important questions. First, what can a LCA be used for? The LCAs have various applications. They are often used to support business strategies and product or process design. For instance, you can identify steps in manufacturing that need to be looked at, or compare different materials. But they are also used in education and support policy decision making. In recent years, they are also becoming more important for labeling and product declaration. The second question is, how can machine learning improve lifecycle assessments? There are, from our point of view, two significant advantages that machine learning applied to LCA models can offer. First, increased speed is one of them. The main advantage here is that a much wider parameter space can be analyzed. For instance, currently models mostly consider only very coarse geographical resolution, taking averages over countries or continents, even though the location of use or manufacturing can play a very important role. Machine learning models could allow to give a higher resolution. The second advantage is the possibility to share trained models very easily. Often LCAs rely on proprietary data or process flows that are confidential and can therefore not be shared. Training machine learning models to replicate the LCA models allows the researchers to share their working models with other interested parties without the need to disclose any of these informations. So even though there are advantages in using machine learning in LCA, unfortunately there haven't been many advances in this area in the last years. We think one of the main reasons for this is that there aren't any datasets available, especially none that machine learning practitioners can easily access and use for their purposes. So our contribution, therefore, aims to provide such a dataset. We present a dataset based on the open source LCA model calculator, which provides a parameterized LCA model for passenger cars. We also show and share the data generation process so that other interested parties can use it to build their own datasets of calculator or other LCA models. The dataset itself has about 700,000 entries with 75 different parameters that are available from the calculator tool and can be used to alter the impact results. It is available on GitHub together with Python code to easily load it, and it has the following schema. The inputs are organized in a 2D matrix, and the results are stored in a 3D matrix with the different attributions in the third dimension. So how is the data generated? For each of the input parameters, so these could be things such as engine efficiency and lifetime kilometers or base glider mass, as you saw earlier, a range of realistic parameters is modeled via uncertainty distributions. These distributions are based on literature values and car specification databases, and they are already present in the calculator model. Now we sample from these distributions to get a set of parameter input values that are realistic and that can be used to model from the model to get results. And the results in this dataset are calculated using the calculator tool and the recipe 2008 method. So the recipe 2008 method is one of these standardized calculation tools to get from the chemicals to the final results. We already started to try to fit some models to this dataset. Here are the different results using a 60-20-20 train validation test split. We compare the different models using the R-squared value. So the R-squared value is the proportion of the variance that is explained by the model. It goes from -∞ to 1, where 1 is the best possible result. The R-squared would be 0 if the model would always predict the expected value. We also compare the calculation time, which is the time it takes to come to a result given a single set of input parameters. The models we analyzed are linear regression as a very basic baseline model, a random forest containing 100 trees, and a 2-layer neural network with 600 nodes in the hidden layer. And as you can see, the results for both the random forest and the neural network look excellent. It gets interesting when you look at the calculation time. Here you can see that the neural network is 4 orders of magnitude faster than the traditional approach using calculator. The random forest is slower, it makes it up in training time, but still almost 2 orders of magnitude faster than the calculator model. In future work, we plan to create a toolkit that can take a parameterized LCA model and directly generate a dataset from it, as well as a trained machine learning model or many different machine learning models, so that it can be useful for both LCA and machine learning practitioners. We also plan to investigate other areas beside passenger cars and further introduce the LCA problem to the machine learning community. It would be great if there are better methods will be developed for these problems. So this is the end of my presentation. We'll leave you with this slide.